data management, we moved from imperative to declarative. So previously, before database management system, developers, they need to worry about the how, and they need to program the how themselves. In their program, they need to write code and routines and functions to read and write from files and manage files, and they are on their own when it comes to database management, when it comes to data management. And data management is not easy at all, mainly for two reasons. What are these two key reasons why data management is hard? Two major key reasons. If you want to address them yourself, very challenging. Two major challenges.
Concurrent data access.
Thank you very much. Concurrent data access. You want to allow your data to be accessed concurrently without introducing any anomalies, without having lost updates or dirty reads. We will see what this concept means as we move forward. Without overriding each other's updates. That's challenge one. Security, yeah, it is okay. We can manage that. It's not as critical. It's not as hard. You basically, before somebody access something, you check whether some kind of access control list, whether they have access or not access. It's just a kind of verifying permissions. It's not as challenging as addressing some problem like multi-user access to the same piece of data without introducing anomalies. What's the other problem? Sorry?
Recovery. Like when there is a power off or something.
Oh, yeah. Failures. Yes, dealing with failures. Okay? Dealing with while you're trying to update or delete or add, some failure happens. Either hardware failure, network failure, a bug in your program. And you might end up with a partial update. You might be doing multiple tasks. The example I gave you last time. Multiple tasks, you're trying to do transfer of money from one account to another. You debited one account and you didn't, before you credited the other one, some failure happened, power outage or hardware failure. What will happen when the system restarts? Which state we will be in? Okay, if you don't do anything about it, you might end up with partial updates. And this partial update is very, very annoying, unwanted in the real world. Yeah, remember, it happens. It happens to me, for example. You place an order in some website, and then you don't get a confirmation message, and your credit card has been debited. So you got your SMS message saying your card has been debited, but you never got a confirmation from the seller that, yes, the order is placed and this is your order number. This is a partial transaction. This transaction is partially fulfilled. One part is done and the other part is not done. This is very undesirable situation you don't want to fall into. So it needs, if you are using file-based database management system, you are on your own to deal with all these challenges. But when you use a database management system, what are you doing? You're kicking out all these challenges to the database management system. And we all like when we say, oh, somebody else will worry about it. We like this. We just want to, we can focus on something else. Okay, well, all these challenges will be dealt with by the database. So, but more fundamentally, what database are really brought is that the responsibilities of the developer has changed drastically. From doing the how and spending their time writing routines to read and write to files and writing a lot of code and dealing with these failures and concurrent access to the data. Instead, after the database management system came in, what's their role? What the role of the developers? What the main roles of the developer becomes limited to two major roles: building the data model are writing queries in high-level language expressing what they want rather than how to produce it. This is a fundamental breakthrough that was invented by the database model, by the introduction, or specifically by the introduction of the relational model. The relational model by this scientist from IBM, and I showed you. This is the father of databases, Edgar Frank Code, 1970, and he, as I mentioned, won the Turing Award for this idea, profound idea of basically separating from the logical level from the physical one. So as developer, we stay in the logical level. We don't need to deal with the physical level. Okay, physical level, we leave it to the database to worry about it. Is the idea clear? This is in terms of developers. Now, not only the database gives us this ability to focus on data modeling only and on querying using high-level language such as SQL, also it gives us these guarantees that are abbreviated in this acronym ACID properties. So these guarantees are guarantees of correctness. So if I say to you, my database assure me that the data I put there is correct, it means that my database has some mechanisms built in that provide this guarantee. And these guarantees, the outcome of these guarantees is that your database is always in correct state, in consistent state. So this is where we stopped, if you recall. Let's just revisit these guarantees. Of course, as we move through the course, every week, we will be focusing on one particular guarantee and see how the database achieves this or delivers this guarantee. Okay? Now, let's start with the first letter, A, atomicity. What does it mean in the context of database? Yes, please. Yes. Yes, so this is all or nothing, yes? So what's the idea here? What's the advantage of this atomicity? Sorry? Yes, no partial update, plus what the database gives us, it gives us a programming abstraction. So remember, what I mean by programming abstraction, for example, in Java, those of you who did any Java programming, you will find some programming abstractions, such as a file stream. You have a file stream, already a built-in class in your Java framework. You use the file stream, you point it to a path on your disk, and then you start reading from that file. Okay? And this file stream class is abstracting all the complexity and the details of how the reading is taking place. The same thing for the writing. Okay, input stream and output stream. So those are high-level abstractions given to the developers to hide complexity, for example, of reading or writing to files. And in Java, for example, we have another abstraction called socket. And this socket abstraction allows me to read and write to network without knowing anything about ISO model and all the networking layers and all the details. Yeah. Same thing in database. To achieve atomicity, database introduce something, an abstraction called transaction. Okay. So us as developers, if we want to ensure atomicity, all we need to do, very simple programming abstraction given by the database. All I need to do, I do something like begin transaction. And here, I start reading and writing to my database. As many reads and writes I wish to do. What I do here, before I do read and write, I do something like try. You're familiar with try and catch. Yeah, I try this read and write. And then if something happens, some error happens, some exception happens. This exception could be from any source. Hardware, from my program, a bug in my program, some constraint that is violated in my database. One of the writes, for example, it tries to insert let's say, tries to change a balance and it put the balance negative. Database will be upset, say, no, 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 cannot do this. It will throw an exception. And this exception, what will happen here? It will be caught here. This exception will be caught. And what we do? Roll back. Roll back trans. Yes? And now, and then here, if nothing happens, if everything goes well, you do here commit. Make the change final. And then in here you do and here this is begin trans, and here you do and trans and transaction. You see the idea of atomicity, how it is achieved. So the database gives you this high-level programming abstraction called transaction, the concept of a transaction. What you do is you begin the transaction, you do a try, and then you start doing a real read and a writes, and you catch any errors. If anything, any exception is raised during this process, what you do in your catch block, you roll back. What a rollback means? Undo all the changes that I have done, as if this transaction never existed. If everything goes fine in the happy day scenario, commit. Make the change permanent and final. Yeah? Now, database, of course, the poor database has some built-in mechanism to achieve this. Okay? One of the mechanisms to achieve this is a log-based. Database maintains a log of all the changes. Log is basically recording all the changes that happen. For example, I changed the row with ID 1, 2, 3. I changed this column. This is the old value. This is the new value. So it keeps a log of all the changes. Okay. If the transaction is committed, those changes will be permanent. If the transaction for some reason is rolled back, then the old value, we have the new value and the old value. We replace the new value with the old one. We undo our changes from bottom up. Yeah, that's basically the idea. Well, of course, we will see the details of this, but I'm just giving you some glimpse. So in here, as developer, our life is much, much easier, and database takes on the hard part of ensuring this atomicity. Is clear? Yes? Yeah. Now, the second one, atomicity, C stands for consistency. What does consistency mean? Consistency, what you define in here, this is consistency in a distributed database. You see, consistency means different things based on the database architecture. If your database is distributed, means your database has multiple nodes, and your data might be replicated. Are you following? Okay. Now, if you query, you might query different nodes. You query node A, I query node B. Same query should give the same result. This is consistency in a distributed database. Yes? So you see here what I mean. The terms are the same, but if you change the architecture, even the meaning of this term will be different. Consistency in a traditional single node database, what does it mean? In a very precise way. Yes, please.
If there is a condition that it should be applied, like if the data should be not less than 0, it should not be less than.
Okay, very good, yes. So in database, when you create your tables, for example, you can define what is known as constraints. Constraints. For example, constraints, as you mentioned, let's say you have an account table, a bank account table. So account will have ID, name, address, phone number, and one of the fields will be balance. In that, you can put a check. You can tell the database, please always make sure this field is never negative, for example. Okay. So now, in this transaction, somebody updated somehow the account and set account balance equal balance minus 5,000. Okay, programmer, they just did this operation. And then database, when it executes this operation, it says, oh, there is a rule here. It says this field should never go negative. And then it throws an exception. Of course, exception is caught by the try and catch within the begin transaction, and the whole transaction is rolled back. But what I mean by this consistency, in simple terms, you can define some rules in your schema, and these rules are auto-verified by the database. If they are violated, an exception is thrown, and hopefully your programmer have done good job in doing their begin trans and end trans and did proper error handling, and they should have rolled back the changes. Yeah. Another example could be what is known as a referential integrity constraints. For example, if you have a customer and order, So order, you cannot create an order without a customer. It doesn't make any sense. So if somebody tries to create an order for a customer that does not exist, what the database will say? No, I cannot do this because there's a constraint here. Because the model tells me that the relationship between the customer and order is a one-to-many relationship. And an order must have a customer, otherwise it doesn't make sense to have an order. You get the idea. These are constraints that you can define in your database, and these constraints ensure consistency of your database. And these constraints you put in place, do you worry about verifying them? No. Who verifies them? The database takes care of the verification, and hopefully you put enough constraints to ensure that your database is consistent. Database consistent means it makes sense. It reflects the desired situation in the real world. We don't want to end up with, in a company, we don't want to end up with an order. We don't know who the customer of this order. Yeah. We don't want to end up with a course and we have a grade for some course and we don't know who the student is. This grade is for. Okay. Somebody inserted a grade for a student that does not exist in our student table. We will have a problem. Yeah. So that's what consistency really means. Okay. Now, isolation. What isolation means? Okay. Very good. Yes. So isolation here means the database gives me the illusion as if the database is for me and only me using it at a particular time. My changes are isolated from changes that are done by other transactions. Yes? And also the transaction, if a transaction is ongoing, still ongoing, and did some changes, those changes should not be visible by others until when? I commit. Database should not allow others to see intermediate results or intermediate changes. Why is that? Why this is important? Because it might be because the transaction might roll back. And if somebody reads your intermediate non-committed changes, what they will have at their hand? What do we call this situation? A dirty read. You read something, and by the time that thing that you read is not committed, it has been rolled back. Yeah. So, for example, let me give you an example. Let's say I have a system that pays people their payroll. So this payroll will go through the employee table, take their salary, and write a bank transfer for them. Okay. So imagine this payroll routine is running. At the same time, some manager decided we want to give a 5% increase to everyone. Okay. So while this 5% increase is ongoing, this payroll should not pick up the changes that are still not being committed yet, because for some reason this 5% increase it might be rolled back, and suddenly this payroll might pick up a higher salary and pay it. And maybe this transaction will be rolled back later on. So what I mean here, the isolation means two things. I am using the database as if it's only me using it. Nobody is competing with me or concurrently using. It gives me like my changes are isolated from others. And the other thing is I am not able to see transactions that are in progress or changes that are in progress that are not committed yet. They should not be visible. Okay, so database uses many ways of doing this. One of the common ways, it's called lock-based concurrency control, or a lock-based mechanisms. And we will see this in more details. Yes? The final one, durability. What durability means? Yes, once the database says, once you say begin trans, do all these changes, commit, and the database says yes, successful, database gives you a guarantee that your change is permanent. Even if the server shuts down after commit, because remember, sometimes database, for performance reason, it writes things in memory, it doesn't push them to disk immediately, okay? Because the disk read and write is the most expensive operation in a computing system, especially traditional ones. So it tries to do things in memory, okay? And then at certain stage, it pushes these changes to disk. But at the same time, it needs to give you the guarantee that even if the power goes off, the changes in memory will not be lost. You see there's a bit of contradiction here. How do you think the database does this? By maintaining a log. Remember log? I just mentioned the log. A log-based recovery. This is called the log-based recovery. Okay? We will see this in much more details. Yes? Now let me give you just how when the database technology changed, even this durability property, the meaning of it changed. In a distributed multi-node system, in a clustered database, what do you think durability means? Is it enough to just one server to say, yes, your changes has been saved and your transaction is successful? Is this the notion of durability in a distributed database? Yes, if your database is replicated, so in a distributed partitioned database, your database could have multiple copies. Okay, so when I for durability purposes, I need to get confirmation from at least a couple of nodes before I tell you that your commit is successful. Okay, so in a traditional database, durability means if the transaction commits, you have guarantee that your change will not be lost. But in a distributed database, that guarantee it's much more than that. It gives you a guarantee that multiple servers or multiple nodes have given their kind of seal or given their approval or given their confirmation that they got the change and they persisted the change. Yeah. So that's what I mean. Some of these notions, you will revisit them while doing your review, and you will see their meaning and the mechanisms of achieving them is very different than in traditional single node, single server database. Yes? But those notions are one of the fundamental concepts in database world. But the mechanisms to achieve them and the meaning of them keep changing as we move forward with database technologies. Open the box of the database and look inside and see how the database looks like. First of all, before I go into further details, when you hear this term architecture in the context of software, because database at the end of the day is a software system, happens to be a complex software system. When I say architecture, what does it mean? When you hear this term architecture. And by the way, it is important when you start studying systems, especially the ones you will be studying in your research papers. One of the things you should quickly try to zoom in is some kind of architecture of the solution. or architecture of the system. Basically, when you hear the word architecture, is what are the components of the system? What are the components? And how this what is the role of each component? And how these components interact with each other. This is what an architecture is. And usually an architecture, each component has what is known an interface through which it communicates with the outside world. So all the complexity of that component is hidden behind a simple interface. So before you dive into the inner working of whole system, you ask yourself, what are the major components? What's the role of each one? What's the interface exposed by each component to the rest of the world? And how these components interact with each other. So architecture is something very concrete in software development. It's not a fluffy word. It means nothing. Really very concrete. Architecture is what are the components of the system, the interfaces exposed by each component, and how these components are connected and interact with each other. Okay. Now, before I show you the architecture of a typical system, of a typical database management system, when you want to build a database management system, you are basically faced with two major challenges. What are these two major challenges? Based on the discussion we had, what do you think? Sorry, the concurrency. Yes, in general, like when you want to build your own database management system, what are two major challenges you will be faced with? In general, handling or delivering the ACID properties is one of the biggest challenges. What else? Performance. And the performance. Performance of what? Of the queries. Given a large data set, not a small database, in a large database. So basically, these are the two challenges that you will be faced with. Achieving high performance on a large database and handling the ACID guarantees. Those are the two major challenges that you'll be faced with when you are building this black box. Of course, as a user, you just enjoy the black box. You don't need to care. But as an engineer or a developer of a database, you should care. Now, if we open this black box, you will see lots of components. But the critical ones, the most important ones, are these two major components, the heart of the database. One is called the query processor, and the other one, the storage manager. Okay? What do you think the query processor will do? What is the role of the query processor? Yes, please.
The query processor means, for example, how the application deal with the store. Okay. For example, read from the catalog how to deal with the function to read the store.
Yeah, almost, yes, but very concrete, in very concrete way. This component, what does it take as an input? What does it produce? It takes the query in very high language and then translates it into a physical plan, a set of physical operations, file input-output operations to produce the desired results. Okay, so that's the role of the query processor. In a little bit more details, which we will see as we move forward in much more, just to give you an idea. So the query written typically in SQL goes through the first step, which is a parser. So this query gets translated into a tree structure. Okay, and this tree structure will be using a relational. It will be at the end of the day expressed as a relational algebra expression. Another thing I didn't tell you about databases. Databases are one of the success pillars, or one of the pillars that made databases so successful. They have very, very strong mathematical foundation. So the relational model is linked directly to the relational algebra. You can bring a textbook and see the operations that you have in relational algebra, you find them implemented in database. And this relational algebra, in math, they have some simplification mechanisms, some optimization mechanism you can take advantage of. This area of database, as we will see when we start looking in details how a query is processed and executed, you will see the role of math directly influencing this component. So to summarize, this query that is textual, it becomes some kind of tree, and the nodes of the tree are algebra expressions. Then you use some mathematical rules that's given by relational algebra to optimize this expression, mathematical expression. Once you optimize it, then you translate it to a physical plan. Physical plan means the operations that you have in your query becomes physical input-output operations, reading and writing to files. And then from there, you give it to a query processor that goes and do this read and write operations on the actual files and produce the results. Just to bring the idea a little bit closer, we're not expecting you to really get the full idea now. We will see this in much more details. So something like this is a select statement written in SQL. This query processor, the first step, it translates it into a tree structure. So in here, what it says, these are the leaves of the tree are the sources of the data. In our case, we will have two files. One is for suppliers and one for supplies. Of course, logically, these are represented as two tables. Logically, but physically, these are two files. What we will do with them, we will read this one and join these two, and then go ahead and do a filter on the result of the join, and then from that filter, after we filter, we will produce the desired output, which is in this case just we want to extract the name, the S name. Okay. Now this is a logical plan, and then for each operation, we decide the physical way to do it. In here, for example, for the supplier, we might do full scan. Full scan means I take the file and read it from top to the end, from the start to end. And I take the second file, read it from start to end. And for the join, how we will do the join? Using a nested loop. Using a nested loop. I will read the first file. Okay, let's say not one line at a time, one block at a time. And then for each block, I read the whole file, this supplies file, and I do the matching between the two. So physically, of course, this is very naive algorithm. There are much more sophisticated algorithms we will see. So in the physical plan, I decide exactly how I will run this, how I will run the query, what algorithms I will use in each step. That's what physical plan means. And then the query executor, it's already have these functions implemented. It just goes ahead and executes them. So this is in high level what really goes on in this query processor. So within this query processor, you can see here we have four major subcomponents. We have the parser that translates the query into a tree. We have a query rewrite that translates it into an algebraic mathematical expression that gets optimized by the optimizer. And then the optimizer also selects which algorithm will be used to execute each step in the tree. And then the final tree is submitted for execution to get the results. Of course, we will go through in much more details for each of these components. So I think we spent 1 or 2 weeks just on the query processor, how it works. Yeah. Now, if you do this in your in-memory database, the query processor and the mechanism it uses and how it works is very different because there is no disk there. The design constraints and the design constraints that we have in disk-based databases are very different if we use an in-memory database. So same concepts, but they will be done in a very, very different way. Okay. Now, the other layer or the other components we have in the database is the storage manager. And the storage manager takes care of the physical storage of the data. At the end of the day, your data will be stored in files, and in these files we will store records. There are many ways of storing files and handling files and storing records in the file. So the storage manager takes care of that. The storage manager also has this buffer manager. What do you think? What this buffer manager does? Sorry? Yes, so when you read data blocks from the disk, you know the I/O operations are very expensive. So you don't just read them, use them, and get rid of them. You keep them in memory for as long as you can. So how long we keep them? When do we get rid of them? Which ones do we get rid of them? We get rid of first, and so on. All this management of memory that is used by the database is the role of the buffer manager. It knows how to read from disk, how to keep things in memory, and how to write back to disk. Yeah. Then we have these two very major components in traditional relational databases. We have a lock manager. What this lock manager do you think will be doing? Managing the concurrency control, making sure my changes do not get override by other people's changes. Make sure that your transaction, when it is running, it's the changes of your transaction that is not committed yet are not visible to me until they are committed. All those, not consistency, the isolation, the I in the asset is mostly implemented in the lock manager. Yeah, we will see the details with the algorithms as we move forward. Now, for example, if you use in-memory database, there is in many no-memory database, they don't have any lock manager. They have completely different mechanism to achieve isolation. Yeah, so same problem, different way of solving it based on the architecture. Because in here, what I'm showing you here, this is the typical architecture of a disk-based database, not in-memory database, not stream processing database. You see here, different architectures have different components.
The stream database doesn't have buffer manager?
It will have different, I didn't explore it too deep, but what I mean, it will have different components and different ways of doing things.
Okay, can you please repeat what lock manager, for example, like what?
The lock manager does, okay. The lock manager, for example, if I want to change my phone number, I'm an employee in QU and they give us a form. Whenever I change my phone number, I go to that form and change the phone number and then submit it to update the table to say my phone number is changed from this old number to the new number. Okay, so the lock manager, just before I do the updates, what it will do, later we will see the details, it will take that particular record I'm trying to change, and it will take an exclusive lock on that record. Nobody should read or write to that record until I am done. Yeah. Once my change is done, then everybody else can see it. So the lock, and there are different types of locks. There is exclusive lock, shared lock, and so on. We will see the details of this later on. So locking-based concurrency control is one mechanism of achieving isolation. Only one mechanism. There are other mechanisms. You got the idea, yeah? Now the log manager. What do you think the log manager does?
Durability.
This is the one that achieves durability and atomicity, both. Sorry? Yes, when the system crash and there are some changes in memory that hasn't been pushed to disk, when the system wakes up and restarts, it goes to the log and says, what are the changes I have that are committed but not yet reflected in the actual tables? It goes through the log and replay the log. And then it goes through the log and say, what are the transactions that started but not committed? What the log manager will do? Roll them back. You see the idea. So the log manager is a critical component for it achieves the two letters from the asset. Atomicity and durability. Yes? Of course, I am just giving you a glimpse of each of those components. We will go through in details each one 1 week at least. Yes, please.
So where is the log manager should be
Sorry,
We
what
store
the
it on the disk or
the log? No, in disk.
So if we store all the logs in disk, it will take time for reading.
Okay, very good question. You will understand this as we move forward. But basically, it's much more expensive to store or to update blocks of the file storing the data rather than the log. What I mean by this, let's take the example of changing the phone number of my record, of my employee record. My employee record might have maybe 100 fields. First name, last name, address, all my details. But what did I change?
The number.
Only the number. So what do you think the log will have?
No.
Just one simple statement. It can be even the update statement. Say the record ID in the table, record 123, the phone field, old value, new value. So record ID, field name, old value, new value. So the log is much more cheaper to persist compared to persisting or changing the whole record in a table. And you will understand this even deeper when we move forward, maybe hopefully from next week, where we'll see database does not change one record at a time. It changes one block at a time. Anyways, the story is there's much more to it. But you see here the database is trying to have this trade-off, this balance between performance by keeping things in memory as much as possible and between the durability guarantees it gave to others. It gave to the users of the database. So it had to keep this trade-off. And it uses some smart mechanisms to achieve this. Is clear? And don't forget, the log manager have changes of multiple tables in the same log. It's fine. We club all these changes and we persist them to disk. We don't need to change the actual tables on the spot. We change it in memory, of course, but not on disk. On disk, we'll change them later. But we know how to reconstruct the changes based on the log. This is just a glimpse. You will see the details of this. In fact, you will be doing some exercises by hand, some scenarios that you will be applying those algorithms that the database does to recover or to achieve atomicity, for example. Yes, please.
The log will keep only the latest one?
No, all the changes. Yeah, all the changes, yes. But at certain stage, you can do what is known as truncating the log. Once you reflect the changes on the data, on the actual data, then those logs are useless. You can truncate them. So, but there is one part of the log that is not reflected yet on the actual data on disk. That part is the critical part.
I mean, most of the changes to the same attribute. For example, if you change your phone number several times.
Okay.
Will it keep all the changes?
Yes, for redo, it will start from top to end. So the last change will win for redo. Yes? And for undo, from bottom up. So it takes the log and traverses the log twice. Top to bottom, this is the redo. And then undo is bottom up. Yeah? So basically, yes, there are some more details about this that we will discuss later. And the log-based recovery and a log-based atomicity is just one way of doing it. There are many other ways of doing it. This is something called multiversion concurrency control, time-based concurrency control, many mechanisms to achieve this atomicity and durability. Yes, but now I'm just giving you a glimpse of those major topics so you are at least aware of them. So we will dive deeper into them and you will start looking at them from the topic that you will be starting to explore on your own in your review paper. Any other question? Yes, please.
On this algorithm, for example, the same for augmentation, like the same for SQL Server Oracle, or would be different?
No difference. That is the competitive advantage of each of them. Of course, what we see here is the common ones, but there are some secret sauce even we don't even know. But there are common ones that are widely known, and you can see it's well known. For example, Oracle, let's say, uses lock-based concurrency control. For example, MySQL uses multiversion concurrency control. They are well known in the literature, and they even declare the vendor declares which algorithm they are using. So every database chooses their own flavor of doing things. And that's what's the competitive advantage. So they all do the same, but with different performance and quality and scalability and different. The asset guarantees are all achieve the same thing. Otherwise, they cannot call themselves a relational database. But how they do it in terms of performance, in terms of scalability, that's what differs between those databases. Yeah, but in terms of functional attributes and guarantees, they all deliver the same guarantees in a slightly different ways. Okay, any other question on the architecture? Okay, now moving on. This is a summary of what really the features of a relational database. So it allows us to persist some data while making it accessible concurrently by multiple users, preserving consistency, and providing fast access. So all these features are given by the database. If you choose a file-based data management, you are on your own. Everything you have to do yourself. That's basically the main idea. Now, you think with all the power, all the innovation and all the smartness of relational databases, you think they will not have kind of a competitor. They will not be challenged. But they have been challenged, especially from the year 2000 and above. It has been really the relational. Before 2000, relational database was the de facto standard. If you think about database, immediately your mind goes to relational. Okay, but from year 2000 and above, things has changed drastically. This is not to say relational databases are not important. They are still dominant and still very, very powerful and very widely adopted, especially for domains that require strong asset properties, like financial domain, order processing domains. Those are predominantly still dominated by relational databases. But in many applications, you don't need to stick to relational database. There are other choices. Okay, so first, and these choices have been kind of brought along by two major movements trying to challenge the relational model and try to challenge the relational database. The first movement started in 2000, around 2000 and above, called the NoSQL movement. Say, we don't want relational database, we don't want the relational model, we don't want SQL, we don't need ACID for all cases. We can live without those. That's basically how the revolution starts. And this produced a lot of alternative data models, alternative databases, alternative guarantees than the ACID. Then the counter movement came, which is known as NewSQL. What the NewSQL says? No, we still want the relational, we still want ACID, we still want SQL, but this time we will re-architect the whole database engines to make them compatible with 21st century hardware and to also make them able to run web scale workload and to handle large volume of data and large number of users. Okay, so, and then we end up, at the end of the day, the reality is what I can call, there is no one database. It really depends. You really need to look at your application requirements. You need to look at your requirements and make the right choice. So first, let me try to explain quickly what are the things that started this NoSQL movement, why people start challenging the well-established billion of dollars businesses and models and industry, and saying, no, let's put an end to this monopoly and dominance and let's explore alternative ways. So what triggers this change? Or what triggers this movement to take place? In one word, the big data, yes. So basically, the scalability needs. What scalability means? What does? That is a solution. That's one solution to achieve scalability. But what is scalability? When you hear this term scalability, what does it mean?
Can be scaled, for example.
Yeah, what does that mean?
Scale up, add more.
Those are mechanisms. Adding more resources to a server or breaking the database into multiple nodes in a cluster. Those are mechanisms. What are we trying to do when we do that? When we add more resources or when we split our database in multiple servers? What are we trying to achieve? Either better performance, or
The storage accessibility.
what do you mean accessibility? Yes, please.
For example, the query becomes fast, the results, I can get the results fast.
This is the desire of having better performance. Yes, that's one driver, but it was not the main driver. Databases already give good performance.
Can search, for example, many tables.
A database can do all of this. You mentioned something to do with big data, yes? So basically, in this context, what scalability really means? The ability to handle large volume of data. You have large data sets, cannot fit on one server. By the way, if your data fits on one server, most likely go with the relational database with closed eyes, most likely, okay? Now, that's one part, because what we have when application get exposed to the web and the adoption of the web increased and the mobile devices came in also, the volume of data being collected increased substantially and the number of users also increased substantially. So we have two problems that came along from year 2000 and above. We have much larger number of users, especially some startup, they get very surprised. Suddenly they start with 1,000, 10,000, and then they go to millions very, very quickly in no time. And those millions, they start pumping and pushing data. Before it was one way, maybe the company is pushing data to the public. But now it's two ways. The public is also pushing data to you, and this data is becoming larger and bigger volume and bigger velocity. The speed at which this data is coming to you is much, much faster. And at the same time, you have a larger number of concurrent users. Yeah. Now, for servers, for the relational database, they started their life in the 70s, which means they were optimized. All the algorithms and the whole engine or architecture is optimized for what? For a single node. In one computer, you install the database, you deploy your database there, you put your data, and you get your applications to start reading and writing to database. It works perfect. Yeah. Now, once the volume of data goes bigger and the number of users increases, how can you, and you want to keep your performance to an acceptable level. You don't want people to request something and go and make a copy, come back to get the results. You know how people are patient these days. They want everything quick and fast. Yeah. So you want to maintain the desired performance and the good user experience. At the same time, you want to handle this larger volume of data and larger number of users. So what is the solution? First, if you want to stick to the relational database, what's the solution? Invest in more powerful servers. Call IBM, HP, and Tell them to bring their latest servers, of course, expensive servers and so on. Yes, you have the money, you don't care, no problem. That is known as scale up. Same server, you keep beefing, putting more resources there, more memory, more disk, more CPUs. Is this beefing up and upgrading this server, is it unlimited? Or you will hit certain limits at certain stage. At certain stage, you will hit certain limit. And then what you need to do? Scale out. Those algorithms that we discussed and we will discuss, those are 50 years of research and development. They squeezed every little bit that could be possibly squeezed. You cannot push them any further. You can, but you have to think out of the box, beyond the original relational model. Yeah, and that's what triggered this NoSQL movement. Okay, and the idea here, instead of scaling up, what you need to do, what is known as scale out, or horizontal scaling. So instead of sticking to one server and starting and investing more on getting the best servers and so on, you just use commodity servers that you can just buy, normal servers. But you have many servers. And then now you're faced with the challenge. The relational model and the relational database were designed and work best when you are dealing with when it is managed in one single server. Once you want to break it into multiple servers, then there is more administrative overhead and there is more development effort. So what you need to do, there are two things you really need to do to handle this scalability. One is, as I mentioned, scale up. What scale up means? Add more resources to the same server. At certain stage, you will hit the physical limit. There is physical limit, you cannot go beyond. Then you will be forced to do what? Scale out, which means you build a cluster. Your database will become a cluster of machines, multiple machines acting as one. Okay? Then basically to scale, you are faced with two things you need to do. One is partitioning. Another word for it is sharding. And the other one is replication. These are the fundamental ingredients of scaling out. So what do I mean by partitioning or sharding? What is partitioning? Partitioning.
For example, tables to small tables.
Small tables. For example, you have a customer. You are Amazon, as an example. Amazon doesn't have thousands, they have millions or maybe billions, I don't know, of customers. There's no way you can fit it on one server or manage it effectively on one server. You need to chop it into multiple tables. Let's say the A is one table or one file on one server. The A is on one server. The B is the name starting with B, another server, and so on. Okay? This chopping is not easy in relational database. For example, here in this region, the A's, you will have skewed data. Lots of people will be starting with A. You have to really think very carefully about how you partition your data without creating hotspots. Yeah? Not only this, your application now needs to somewhat change to read from multiple servers, join the results, and produce the final results. Okay? If you have a query, for example, give me the customers in Doha. Good luck doing this. Before, when you have one server, you push it to the database, it does the query plan, produce the result, and give you the results, and that's it. Now that you partitioned your database, it's a different story. You have to run the query in multiple nodes, because your customers living in Doha, they could have different names that starting with different letters, so you will need to visit multiple nodes. So this is feasible, of course, using relational database, but more effort in terms of development, more responsibilities on the shoulder of the developers, and more costly to maintain and more costly to set up and so on. It's not designed for this scenario, simple as this. Yes? So partitioning, what partitioning will help you to solve?
The big data.
Thank you very much. The big data problem. If you have a large table that you cannot fit in one server and manage effectively on one server, to handle the big data side of the problem, what you do? You partition. But you need to partition carefully. Okay? In SQL, in relational databases, is partitioning built in as one of the features of the database? No. This concept of partitioning not even in the mind of the designers of the relational database, let alone the relational model. Okay? Now, this partitioning, will it help with a large number of users? So let's say people that are asking for customers in Doha, and your customers in Doha are spread in multiple tables. Will this help? It might even make it worse, because you have to hit multiple nodes and there is a network in between, and you have to aggregate these results and give them back to your users. So to handle the large number of users, besides partitioning, what you need to have? Replication. What replication means? Same data, multiple copies. I'm sure all of us have experienced this. When we have multiple copies of the same document, what happens? What is the problem you face immediately when you create multiple copies? No, I want you to use, now storage is not a problem these days. I want you to use the correct term. No. Once you replicate your data, immediately you face one problem.
The same should be the same.
Which is? Consistent. So basically, once you replicate, you face the problem of keeping these copies or replicas in sync. You need to keep them consistent. So because when you have multiple copies, what this allows you to do, you can route reads to multiple servers. So if you have let's say 1,000 reads coming and you have 10 copies, you divide the load. 10 copies, every server will get 100 reads. Yeah, instead of sending all the reads to one server. So you need these two basic ingredients or basic mechanisms for handling scalability. Both the partition and sharding will help you to handle the big data problem. And replication will help you to handle what? The replication. No. Consistency is the price you need to pay once you go for replication. Yes? No. No, more important, why do you replicate usually? For two reasons. One is performance. No, those are costs you need to take care of, or those are problems you need to take care of. So two things you gain. One is performance, because not all users will come to one copy. You can distribute users to multiple copies. Yes. So your performance will be enhanced, and your scalability will be enhanced. You can handle more users because you have multiple copies. Simple as that. Yes. Now, not only this, you also have what is known as high availability. What this means? What this high availability means? If one server fails, the whole system will still keep running. Why? You have multiple copies. Okay. What is the cost you pay? Making sure these copies are consistent. Are you following? Okay. Let me summarize. Okay. In around the years 2000, the relational databases were really challenged, and these challenges were triggered by the need for higher scalability. Higher scalability to handle two things: the increasing volume of data and the increasing number of users. Yes? Now, the relational people, the Oracle, try to defend, oh, you just need to buy this server from us or from HP or from IBM, you will be fine. Yes, you can do that if you can afford it. You can keep doing that, but at a certain stage, you'll definitely hit the physical limitation. And then you have no choice but to build a cluster, multiple nodes to manage and store your database. Yeah. Now, when you have a cluster of machines, now you need to do two things. Two mechanisms you need to use. Partition your database into multiple parts so you can host them on multiple nodes. And also replicate, have multiple copies of the same data. So partitioning, what's partitioning help you to do? Handle the big data problem. And what replication helps you to do? Two things. Better performance and higher availability. Higher availability. If you have a single node, single database node, you have what is known as single point of failure. If your node fails, your whole system is down. But if you have a replication, then if one node fails, because you have same copy in another node, your system can still keep going. Of course, with degraded performance, because you have less workers now than demand. But at least the system is still up and running. It's not failed completely. Okay, now, these two mechanisms, are they built in relational database? Not built in. Do the designers in 70s, the IBM and its sisters, when they designed and built this database management system, they have these concerns in mind or these problems in mind? No. So you have to kind of do some gymnastics and squeeze here and there to be able to do this, which become costly, more complex, and so on. Okay, that's why the no relational movement came in. And what do you think? What is the core of this no relational databases that keeps on popping up? What do you think? What will be built in by default from day one? It will be built in these NoSQL databases out of the box. Partitioning and replication is built in the new NewSQL database. So scalability and performance is much, much higher high priority than other attributes. You got the idea. So they say if scalability and performance is higher in your priority list, and asset you can live with not so consistent, something called eventually consistent, okay, then you might consider no relational database or a NoSQL database. Not only this, they will say, okay, the relational model where you have entities, relationships, and you have tables with relations and the SQL to query them, forget about it. We will give you some other model, another data model, other than what you are familiar with. Okay, so the NoSQL movement came along to really address the scalability and high performance. And along the way, it suggested a new data models to represent your data. So now with this introduction, let me just show you quickly, very super quickly. First of all, the types of NoSQL databases that's popped up around 2000, many products, but they can be categorized in these 4 categories of databases. The first category, it's called the key value store. Key value store. We all familiar with hash tables, yes? In Java or Python or any language, it has hash tables. How hash tables work? We have basically a key and a value. And the only operation these databases know, I can add something by key. I can add, this is the key, this is the value, and I can retrieve it. I give you the key, you give me the value. Okay? The value is black box. The value could be anything. Could be a simple integer, could be an array, could be a document, could be whatever. So the whole database, imagine the whole database becomes like a hash table, distributed hash table, can be hosted in multiple servers. But the database now, the limit, it's a totally different data model. There is no relationship, there is no joins. You cannot query the value. You can only query by key. That's it. Yeah. So let me give you an example where this could be very, very useful. For example, if you go to Amazon as an example and you start putting your items in the cart, okay? So every user on Amazon, when you log in there, you will have a session ID. So you have a session ID unique to that browser session, and associated with your session ID will be your cart. Or it could be your preferences, could be a lot of things related to your session ID. So basically, when you come back to Amazon, all they do, they know your session ID, they store it in a cookie or they store it somehow to know who you are when you come back. And then when you come back, they just do one lookup. Go to this key value store and say, give me all what I told you before about this particular customer, and you get back your card, you get back your preferences, your previous product that you have liked, the recommendations that Amazon is giving you, and so on. So it's basically one key in this scenario, one key which is the session ID, and the value could be really anything. An array could be a simple value, could be the color that you preferred. Let's say the background color of the website, could be whatever. Okay, so that's the idea. And here, this is the most simplistic data model you can ever have. Just a key and a value. Yeah?
Yes, this it's not there in the SQL one?
With SQL, you can do whatever you wish. But do you have this out of the box? Do you have this and this?
No, I mean the key story here is not there in the SQL one.
No, in SQL.
You have like the keys that unique for every.
No, but the fundamental concept in relational model, you have entities and relationships between them. For example, you have, let's say, a customer has order, and order has order items,
yeah,
and
but
order.
But every entity you say that it has like something unique that we can retrieve all the data from that unique.
Yeah, that is fine. The relational model, you can use it for any of this, okay? But it does not have these features built in, okay? You can create one table that has only two columns, key and value. Now, sorry, you cannot really do this in relational. Sorry, let me explain why. The relational, by design, every column is atomic. What I mean by atomic, you can also only store one value. Okay. In here, first of all, the value does not have any structure.
Excuse me, doctor.
There's no schema here. In database, you must have schema. In here, there is no schema at all. Yes, please.
It will not be too much effort for the database that I find I'm looking for data and many small tables.
There's no table here. That is the idea. Because we are still influenced by the relational model, we cannot even think of this. In here, there is no table whatsoever. What do we have in this data model? Not tree. A hash table. You know hash tables? I have a key and a value. Okay? Yes? Of course, this relational model is really very generic. You can use it to solve so many problems. That's why relational databases are there. Almost in every organization have some kind of relational database. It's applicable in many, many scenarios. But this one, for example, has very much narrower use cases where you can realistically use this. Okay, you can use it, as I mentioned, for one use case for it is as I mentioned, is the shopping cart. Is when you want to manage profiles, user profile. So where you have one user, every user have a unique ID. That's your key. And the value is your limit. Your imagination is your limit. You can put whatever there. You can put the color they liked. You can put the shopping cart they have. You can put the pages they visited before. So it's the value is a black box. You can put there whatever you wish. The database does not care. It's a black box. Now, when you come back and you want your data that you stored before, what the database expects you to give it? The key. If you don't have the key, bad luck. You cannot get your data back. There's no such thing as query, group by, join. Forget all that SQL stuff. What the database here, what does it understand? Two operations. What are these two operations? Get and set. That's it. Get, what does it expect as parameter? The key. And then it gives you a black box. It's up to you as an application developer to interpret what is returned as a value. It's up to you. Database does not care what's in there. Now, if you want to change something in the database, set. And what takes two parameters? The key and the value. If the key already exists, it will be updated. If the key is not there, it will be inserted. You see here, the abstraction is totally different. Yes? That's it. That is basically the idea. And here, it's much, much easier to partition, much easier to scale, to replicate, and much, much easier. And there are products in every family. In every family of this database, there are a bunch of products. This is just a limited number. So, for example, in the key value store, we have this. The most famous one is this one, Redis. Very well known, very widely used. There are other competing ones. Is clear? This is a very different data model, different way database works. But still, it's managing data and storing data for us. Okay? And by the way, the value does not need to be atomic. Does not need to be single value. Could be an array, could be a list, could be object. Yes, could be an XML document, could be Word, could be PDF, could be anything. Could be text, could be web page, anything. Anything that you can give it a key, you can store it there. That is the idea. Is clear? The second family of databases is called column family database. Column family database. I think it's easier if you see an example how it looks like. So the key is let's say your primary key. Okay? Your key is a primary key. And then the columns, you can have a name value pair. Name value pair. And the columns, they don't need to be the same. So that's another problem with the relational database. In a relational database, the schema is very rigid. The schema is fixed. You say, this is the structure of my table. All the rows will have the same structure. If some of the columns does not apply, what do? No. You put null in them, but you still have them. There's no escape because the structure is fixed. In here, the structure is not fixed. You can have different structures. And basically, every row has a key, similar idea as the relational model, but there is no fixed schema. It's similar, kind of, you can think of it similar to the key value pair, except in the value, what you have in the value, you have kind of columns, column and value. And you can think of it as rows. They don't need to have the same schema. It's up to you what columns you put for each row. Okay? And then when you look up, same thing. You are looking up using the key, which is the row key, and you get the value. You can also look up by putting the row and the column name, and you get the value just for that column. You can also do that. Yeah. But the idea here, keep in mind, each of these family of databases, replication and partitioning is built in, and running it on a cluster is built in out of the box. Consistency, making sure there's consistency, high availability is built in without any extra investment. Okay, in this family, there are many databases again. Column family, this is Cassandra, the most famous one. There's HBase, there are many others. Okay, The third family, which is really, this is one of the most really the solution that really challenged the relational model and picked up. It has a much higher adoption because it has many application scenarios. Almost any relational database can be converted to a document-oriented database. And the idea here, let me just explain to you the idea in very, very clear way through this example of an invoice. We all familiar with invoice, how invoice looks like. So invoice has some header that has the customer details and the order details. And then it has the order items, okay? So in a relational model, if you want to store the data in an invoice, you have to spread it into multiple tables. So something like this. You will have a customer has one or many orders, an order has one or many line items, and an order has one or many payments. Are you following? Yes? So it is costly in terms of performance when you are inserting a new order. How many tables you will hit? You will store the header here. This is one table. You will store for each line item, you will do multiple inserts here. If you have 100 items in the order, 100 inserts in here. And then payments, if you paid multiple times, because you might pay in portions, or maybe you pay one go, you have one entry. Let's say keep it one to one. So maybe you will have one insert here, 100 inserts here, and one insert here. At least 102 inserts. Are you following? To create one order. And then if you want to produce the invoice, what you need to do? Join all these tables again and write this quite beefy and complex query to bring this data back the way it was. Yes? Now, in the document-oriented database says, no, don't do that. This is known as an aggregate. This is an aggregate entity. This is a good example of an aggregate entity. An order, keep all the information related to the order as one piece, as one object, and store it all in the database and then retrieve it back as one piece. So you will save in terms of the inserts will be much simpler, both in terms of programming and in terms of performance. And also the retrieve will be much, much simpler, both in terms of programming and in terms of performance. Yes? So the idea here in a relational tends to spread and divide and decompose. There are even rules. Those of you are really familiar with databases, there are some rules known as normalization. First normal form, second normal form, third, fourth normal form. What these normal forms are trying to do? Decompose the tables into more tables to avoid redundancy. Okay? In here, no, keep the aggregates, because when you develop softwares, in many cases we have what is known aggregate entity. In aggregate entity, I have a whole and I have parts. So here the order is an aggregate entity. Okay, it has many parts. It has the order details, the order items, and the payment. So in document-oriented data model, it says keep this aggregate as one thing and store it as one thing and retrieve it as one piece. Are you following? And these are known as document-oriented databases. And the most successful one, the most famous one, is MongoDB. Yes, MongoDB there, but there are many others. They are kind of hanging there. MongoDB is the most successful one. Okay, that's the third model, the document-oriented database. The fourth model, it has very narrow niche use case, not very common. You cannot apply it everywhere. Is a graph database. The graph database, in some cases, you might have entities that have relationships between them, and you want to store and manage this data as it is. Okay, for example, in a social network, we have this person have this friend, and this friend liked this item, and so on. So you can, in social networks, as an example, you can store the data about a social network in a graph database, and you can store it this way and query it this way. Okay. So those are. Oh, sorry, you should have alerted me. That's it. Let me just close this one. You got the idea of NoSQL. What are the major things it's brought along? No, first of all, new data models. Relational, it's not the only way. There are other ways. That's the first thing. Also brought along partition and replication built in. Out of the box, you have higher scalability, you have a higher throughput, and higher availability. Yeah, and also you can run it in commodity servers. You don't need to have these sophisticated servers because you can have a cluster of multiple servers. You don't need to go for the most expensive, latest servers. Okay, that's basically the idea. But of course, the price here, you cannot. They don't give you all the assets. Some of them, they give you asset properties. Some of them, they say, no, we cannot give you asset properties. We'll replace it with something else. Yeah. And then, as I mentioned, the NoSQL came in to say, no, we want to keep the relational, but we will fix the problems with the relational and make the partitioning and make replication out of the box, and even run the whole database in memory for you if you wish. Yeah. And now that's another movement. And that's created yet another vague of databases. And that's the future. That's where people are heading. Because now the development in memory is much, it become affordable and feasible to host the whole database in memory and have a cluster of servers, and the whole database lives in memory.